Hi everyone, I am Madam Rosmaya. Welcome to my YouTube channel. In this video, we are going to discuss on line spectra. Okay, line spectra. The evidence of the existence of discrete energy levels in an atom is given by emission of line spectra by atoms. What is line spectra? So a line spectra is a dark or bright line in an otherwise uniform and continuous spectrum resulting from emission or absorption of light in a narrow frequency range compared with the nearby frequencies. One of the use of line spectra are to identify atoms and molecules. Okay, there are two types of line spectra, emission line spectrum and absorption line spectrum. And this is the continuous spectrum. For emission light spectrum, example given here is line spectra of hydrogen and line spectra of helium. And for absorption line spectrum, example given here is dark line spectra of hydrogen. Okay, vapor lamps, example sodium, mercury and neon here, use electricity passing through a low pressure gas to make light. This is done at a much lower temperature than an incandescent light bulb, and the overall color may appear eerie. When you pass this light through a prism, you get a completely different looking spectrum called an emission spectrum or bright line spectra. Okay, why we see three colors in the spectrum of hydrogen? Okay, it happened because example here for red light. So red light is emitted when the electron drops from orbit 3 to orbit 2. And for blue or green light emitted when the electron drops from orbit 4 to orbit 2. And another example is for violet light is emitted when the electron drops from orbit 5 to orbit 2. In order to make this kind of spectra, two things have to happen at the same time. First, there needs to be some object capable of producing a continuous spectra. Second, a low pressure gas has to lie somewhere between you and the object, making the continuous spectra. All stars, including our sun, produce this kind of spectra. Refer to this animation. Light passing through the atom has some of its colors absorbed by the electron. So the electron absorbs certain energies that allow it to jump to higher energy levels with the atom. As the electron comes back down to its original position, it releases the energy it absorbed as color. This color is scattered in all directions, and therefore the spectrum, which travels in one direction, is absorbed. Okay, refer to the animation again. Okay, this is another animation to show the absorption of spectrum. Electron absorb certain energy from light and jump to a high energy levels. The energy that is absorbed appears as black line in the spectrum. Okay, the spectrum form depends on the type of gas used. The dark line pattern is exactly the same as the element's bright line pattern. That is, hydrogen gas will produce 3 or 4 dark lines, which are found where the red, blue, green, and violet bright lines are found in the emission spectra of hydrogen. It's like a reverse image. Okay, compare this spectrum diagram. Okay, the position of the dark lines in the absorption spectrum of hydrogen are the same as those of the lines in the emission spectrum of hydrogen. Refer to this line. Hence, hydrogen atoms absorb photons of the same frequencies as those that they emit. Okay, in this schematic diagram, when a beam of white light here from a filament lamp is incident on a diffraction grating in a spectrometer, continuous spectra are observed. So instead of using prism, we can also use diffraction grating to get the spectrum. For the emission spectrum, when a beam of light from hydrogen discharge tube is incident on a diffraction grating in spectrometer, the emission line spectra of hydrogen are observed. And for absorption spectrum here, when a white light from a filament lamp passes through a hydrogen gas before it is incident on diffraction grating in a spectrometer, the absorption line spectra of hydrogen are observed. So we combine these two in the absorption spectrum, where the gas just now we use in the cool gas instead. So when the wavelength pass from the here, from the continuous spectrum past the cold gas, so some of the spectrum is absorbed. Okay? So that's why we get the dark lines here. So application of line spectra, we can study absorption spectra from stars to understand their composition. So example given here from the sun absorption spectrum, and this is the hydrogen absorption spectrum. So we can compare this and we can determine which gas are abundant in the sun. Example here, the telescope used here is a Hubble Space Telescope imaging spectrograph. So this is from star, for example, and here is a beam of light coming to Earth from a distant quasar, passes through numerous intervening gas clouds in galaxies and in intergalactic space. So these clouds of primeval hydrogen subtract specific colors from the beam. So the resulting absorption spectrum recorded by Hubble Space Telescope Imaging Spectrograph STIS is used to determine the distances and chemical composition of the invisible cloud. So in this case, we study the sun's absorption spectrum and compare with the hydrogen absorption spectrum. And by observing comparing these two, hydrogen is the most abundant element in the sun, and the darkest line in its spectrum match the wavelengths of the absorption spectrum of hydrogen. Okay, that's all for the video of line spectra. Thank you for watching.